All right, so I'll begin with a word of prayer. So, Heavenly Father, we thank you again for this opportunity we have to study your creation. Just pray that you'd be glorified at what we do this day, Lord. In your name I pray, Lord Jesus. Amen. Oh, yes. The attendance sheet. So please. Now, so today I want to talk to you guys about sort of the big picture of physics. Yeah, let me just call it that, big picture. And so, as it stands, there are what we call the four forces. So what are the four forces in physics? The one we've talked a fair amount about in here lately is gravitation. So gravitation is one of the four forces. And so essentially, you know, the latest, greatest experimentally verified theory we have of gravitation is generally agreed upon to be general relativity. All right, so that reproduces Newtonian relativity, you know, in the limits of relatively small mass and so forth. Now, most of, you know, Newtonian relativity goes a long way, like most of the space program, you know, talk about placing satellites in orbit, all these sorts of things, pretty much all just Newtonian relativity, Newtonian mechanics. More to the point, Newtonian gravitation. Just that formula you guys have worked with this semester, GMM over R squared, right? So that's the one force, gravity, but there are three other forces. The other three forces are electricity and magnetism, or you could call it electromagnetism. All right, electromagnetism. And then there's also what's called the weak force. And last but not least, there is the strong force. So let me tell you a little bit more about these. So electricity, electromagnetism is, okay, so first of all, gravitation, if you think about it, before Newton came along, we used to have different physics for, you know, the heavens versus the earth. You know, like the ancient Greeks and so forth, they would have one theory of motion for things that were on the earth, a different theory of motion for things that were up in the sky. You've heard of earth, wind, fire, water, all that stuff. So that actually concerned the different physics of the different things had different physics, you know, and so, but with Newton, he said basically that, well, no, mechanics works the same on Earth as it does for the moon, for the stars, and so forth. I don't know if he said quite that much. I'm not sure how actually far-reaching he had as his vision for it. But certainly there was a unification of physics, terrestrial physics and heavenly physics, in the introduction of Newtonian gravity. And then electromagnetism is actually itself a unification. See, as the word says, electromagnetism. See, there's two things in here. You got the electric field, and you also have the magnetic field. So, like the words sound like, electric field, you've experienced, you know, you take the words balloon, you know, rub it against your head and stick it to the wall, or maybe if you're walking through Walmart, after a while, you reach out to your friend who's walking with you and go like this, you know, because after those rubber wheels have rolled along long enough, if it's not humid enough in there, you can build up quite a charge, right? The joy of shocking people, it's really the highest form of entertainment in Walmart, besides just looking at people, but or employees, but no, they're good. So electricity, and of course you also have electricity, right? Like classic, you have these things called Leyden jars, basically different forms of capacitors that would store charge, right? that all would be associated with, let's say, electricity. And then on the other hand, you have magnetism, right, which we have known about for quite a while. You know, that there's certain rocks that stick to other rocks, and that by bringing like swords and other things close to it, you can also give this this similar phenomena, right? So one of the great unifications of physics was the idea that electricity and magnetism were actually part of a single unified concept. So this, bringing these together, was done in about 1860 or so by James Clerk. Well, let's just say James Maxwell. Actually, I'm not sure it's really just him, and that's ish, added 1860-ish, but he sort of completed the story. It was a story that I'm probably doing an injustice to at least a half dozen people, and probably another half dozen I just don't know about, in the early 19th century, that sort of put the pieces together and realized, oh, wait a minute, this electricity, this magnetism, it's really part of one coherent phenomena. Yeah?
Is the same Maxwell the one from the Maxwell equations you showed us before?
Yes, one and the same. So Maxwell also did things in like thermodynamics, and I mean, he's a theoretical physicist, so he did a lot. Actually, Maxwell's an interesting story in the sense that he was like, I don't know, 50 or 60 when he came up with that major result. So he was somewhat older, which is somewhat unusual. You know, like a lot of times when people have really significant results, you know, it happened like when they were younger than you guys. You know, I know it's kind of depressing, but it's true. There's no hope for me, so I'm just kidding. But so electricity and magnetism actually part together of the electromagnetic field. You guys ever heard of the weak force? Like you've never. So I saw some shaking of heads. So what is it? Nobody? What is it? Yeah?
It's the forces inside of atoms that, well, basically the forces that are not in the nucleus itself.
Mm-hmm.
Electrons being attracted to protons. Is that correct?
I think that's part of it. But of course, like the electromagnetic force also does that, right? Like, I think mostly we, like if you take a course in quantum mechanics, the Hamiltonian you'll write down for like hydrogen-like atoms largely concerns the electrostatic, like the potential energy in the sense of electric potential energy between like the nucleus and the electrons. So I think that's like the dominant force in terms of like orbital, the theory of orbits, and so like those kind of energy levels in chemistry, they're called electronic energy levels. For that reason, they have to do with the electromagnetic force. The weak force has to do with radioactive decay. So this is primarily place we see weak forces is in radioactive decay. So like for instance, in like I was telling you guys about the neutron, the free neutron, you know, a free neutron in about 11 minutes will decay into a proton and a electron and I believe an electron neutrino. Electron neutrinos, those are like these sort of ghostly particles that very, very weakly interact with anything. And that term weakly is actually kind of a technical term, but not, I mean, this is an annoying thing because you can talk about a force being weak, but the weak force is a specific thing, you know? Yeah. It's not a very good name for a force, really. Similarly, the name strong force is a really dumb name. It's like, who come up with these names, actually? Now that I'm looking at them, they're so lame. Like, weak force, strong force, like, what? But anyway, the strong force has to do with the binding of nucleons, right? So there's two aspects to the strong force. This is like how protons and neutrons, you know, bound together in a nucleus. I can't spell. Anyway, nucleus. So, what goes on there? If you think about what an atom looks like, what's it look like? Like roughly speaking, it's something like this, right? You got all this. The nucleus here's like a stupid, totally illegitimate picture of it, but think about it like a bundle of grapes. And then way out here somewhere you've got like electrons, right? Orbiting, maybe. But the thing is, in here you have two different things. You've got neutrons, and let me use color coding, and you got protons. Now, what's a neutron? What's a proton? They're weird names. Yeah, proton is positively charged. That's the main thing. So let's make it red. So you got these protons in here. I'll make them red. All right. And what about the neutrons? Are they charged? They're neutral. That's right. So here's a stupid picture of, I don't know exactly how they're situated. This is probably not physically reasonable. Anyway, all of these things are quantum mechanical. So any of these kinds of classical pictures you draw, they're just pure hubris anyway. But the neutrons are neutral. They're uncharged, whatever that means. We'll find out next semester. And that's not true. That's not really true. Did I ever explain to you what mass was this semester? Not really. It's just something we've worked with. It's a fundamental idea. It's a basic concept in here. It can't really be explained except with respect to its interrelation with respect to other physical variables. In the same way charge is basic. It's something that elementary particles can have or not. If it's a neutral, like the neutron, it has no charge. So, excuse me. What's the scale here? We're talking like microns or something like that. You know, like 10 to the, I forget, I think 10 to the minus 9 maybe actually. I forget the size of a nucleus. I want to say, goodness gracious, I'm rusty. I don't remember the size of a nucleus. Maybe 10 to the minus 10. It's really small. So the electron orbit is like much, much further out, comparatively speaking. It's pretty far out there if you want to think of it. It would be somewhat analogous to like the way the Earth and the Moon are situated, something like that, roughly speaking. The point is, these protons are positively charged and they're super close together. The thing about positive charges and is they what? They repel, right? Yeah, positive charges repel. So how can the protons stay packed together so super close together and yet the positive charges repel? The answer is the strong force. So the strong force is what glues them together, all right? How does the strong force glue things together? Well, it acts via what are called gluons. I did not make that up. Gluons. The force-carrying particle for the strong force is a gluon. Now, there's a substructure to the strong force, and this is probably at the level of the color force, if you want to call it that. So a fancier word for this is chromodynamics, which means color dynamics, basically, right? Chromodynamics, or the quantum version of this is called QCD. QCD, quantum chromodynamics, describes the basic physics that underlies neutrons and protons. Now, protons and neutrons, if I recall correctly, they don't. You think of those interacting with each other not by gluons, but rather by things called pions or something like this, or pi mesons, something like this. So you're like, well, wait a minute. So the strong force, is it gluons? Is it pions? Like, what are you talking about? The strong force is a collective term for like a whole bunch of what we would call nuclear or high energy physics. All right, this is the physics which we understand how the nucleus sticks together. Right. The weak force again has to do with radioactive decay, like uranium changing from one isotope to another, that sort of thing. All of the medical imaging is based on like the weak force, right? You get some kind of radioactive dye, they inject it in your blood, and then they take images of this, and they can basically see your blood because you're glowing because your radioactive decay of the liquid that they shot in you. It sounds real healthy. I would say don't do that too much. Just seems like a bad idea. But anyway, and then so that's pretty much it. This is the standard model. The standard model has the electric, the weak, the strong force, and gravity. Now, there's a little bit more that goes on here that I will explain. So, of course, electromagnetism, well, gravity is probably the oldest because at least the Newtonian part of it, which is, the Newtonian part of it does describe the lion's share of like what we observe in nature and what we experience. So like 95, I don't even, how do you make exactly a percentage? But maybe 98% of our experience is pretty much encapsulated by Newtonian gravity, which we've known since like Newton, which was what, like 1660, 1680, something like that. Electromagnetism, on the other hand, is a little bit more recent. It turns out electromagnetic charge. So gravity is different than electromagnetism in the sense that it's always attractive, right? Have you guys ever watched Fringe? No? Nobody's seen Fringe? There's this great episode of Fringe where people get this anti-gravity and they like start flying off the earth. So they have to wear special boots to like not fly off. It's pretty cool. That is like really foreign to our experience, right? Gravity pretty much attracts, right? Like I don't think we've ever had like really got a hole into this marker so it doesn't like fly off into the sky, right? Like that doesn't happen, But electromagnetism, on the other hand, electricity either comes in the attractive or the repellent sort. So that's one big difference between this semester and next semester, is we have to worry about like charges repelling and unlike charges attracting. The weak force also could either be attractive or repulsive. Now the weak force, I know what I'm getting to here. So the force carrying particle for gravitation is what's called the graviton. The graviton. So you can imagine gravity as a field theory, as the exchange of these things called gravitons, which, if you study the mathematics of it, these are massless spin 2 particles. Now electromagnetism is mediated by something called photons. You've heard of these. So light. Light is the manifestation of electromagnetism, and we understand light to be propagated by the exchange of photons. Photons are spin 1, and they're also massless. The weak force is propagated by the W plus minus and neutral current, the W plus minus and Z. These are the force carrying particles for the weak force. These are massive, so they have mass, and it's very short range. So basically this is the deal. If your force carrying particle is massive, it's very short range. If your force carrying particle is massless, it has infinite range. So gravity and electromagnetism, they go on and on, right? So like the fact that photons go on and on led us to like Olber's paradox that we were talking about the other day. Strong force, gluons, again massive, very short range. And weirder still, the W plus minus Z, I forget the spin of these. I think they're like spin 1 or spin 0. I can't remember. The gluons, I don't remember the spin of those either, sadly. But what I can tell you is that the gluons, they act on something called quarks. And quarks are really weird. What are quarks? So quarks, we think that, yep.
What do you mean by spin 1, spin 2?
What is spin?
Rotation.
Sadly, no. Spin is not rotation. That is an unfortunate burden of being a native English speaker. Is you've already got a prejudice or what the word spin means. But spin is much like mass or charge. It's a particular quantity, a particular trait that we ascribe to a basic elementary particle that describes how that particle interacts with the magnetic field. Saying something is spin 0, saying something is spin 1, saying something spins 1/2, all of these describe a very particular interaction with magnetic fields. So, for instance, the Stern-Gerlach experiment in like 1930 something or other showed that electrons have spin 1/2. So you have ones that are like spin up, spin down. Depending whether spin up or spin down, when they're subjected to a magnetic field, some of them will bend up, some of them will bend down. There's a very particular phenomena that you can see there. The other thing that you can see spin in is when you have composite particles, particles that are built from more than one thing, the spin of the component particles, it adds together through something called the tensor product. So like there's a whole theory of mathematics here, representation theory, which is needed to fully understand it. The long story short of it is that all of these elementary particles, they carry representations of like the fundamental symmetry groups. When you combine particles, you have to combine the representations using something called the tensor product. And that describes how the particles can fuse together. And basically it allows different possible ways you can combine particles. And so that's a good question. Like, what is spin? It's something abstract, unfortunately. So this was one of my friends in graduate school who's Greek. She was rejoicing in the fact that she was not a native English speaker, because for her spin is just this abstract word. It doesn't mean rotation. But it was intended. They thought originally, I think its origin was in the hope that it was somehow related to like spin. But when you carry out that analogy directly, in terms of like analyzing electron motion around a nucleus, you end up with like being off by like a factor of 2. This is a standard calculation in like junior level quantum mechanics, that if you think about the orbital angular momentum of the electrons, it doesn't match what we'd like to think of as the intrinsic angular momentum of the electrons. I'm just making vague statements here, like this is the struggle. Part of understanding quantum mechanics is understanding all this stuff. It's a mess. Yeah.
Since the electrons are not on a circular
I
orbit.
thought you were going to ask me if this was on the final, and the answer was yeah. No, go on. Sorry.
Do they ever collide?
Do the electrons collide?
Ever?
Well, I don't know. I mean, you see, I hear physicists talking out of both sides of their mouth about this. All right, so like, here's the thing. One of the things you learn in electricity and magnetism is that when a charge accelerates, all right, when a charge accelerates, it radiates. So what about when something goes in a circle? Is that accelerating? It is, right? Yeah, v squared over r. We know this, right? So if an electron is in motion around a nucleus, it's always accelerating. So I just told you that accelerating charges radiate. So that electron rotating around the nucleus should always be radiating energy. What should it happen then? It should spiral in to the radius in no time. And yet it doesn't do this. Why? The answer is quantum mechanics, which is not very satisfying, but essentially the point is that there are certain states which are there to go into, and the electron essentially has to reside in the allowed quantum states. And since there is no quantum state below the one in which they're orbiting, they simply cannot radiate that energy, even though they should be, because they're accelerating. There's some like fundamental contradictions between the classical and the quantum, and trying to understand these things is still very much an open project. So, like there's something fundamentally wrong with how we understand quantum mechanics and how we understand gravity. There's like, okay, so these three these three things here: electromagnetism, the weak force, the strong force. They all have, they're all like basically consistent with special relativity, and we can write what's called field theory for these things. So like quantum chromodynamics is the quantum mechanics for the strong force. There's also QED, which is basically the quantum mechanics for electromagnetism. This was discovered by Feynman and Tamanga, like background World War II. The electroweak force, as it's called, the study, like the, I'm forgetting the name, name of the stupid thing, but it's not QED, it's Q, oh, I can't remember the abbreviation for the stupid thing, but the electroweak force is what it sounds like. So around 1970, people figured out that you could take these two guys together and you could put them together, and these two things collectively at a higher energy unify into something called the electroweak force. The electroweak force is what it sounds like. It's the combination of the electric and the weak force. If you're at a higher energy level, rather than having electromagnetism and the weak force, you have the electroweak force, which instead of having the photon, the W plus minus, and the Z, you have these. You have massless. You have I forget. I think they're massless force-carrying particles. Then there's something called symmetry breaking. This Higgs boson enters in. The photon becomes massless. These gain mass. And then the asymmetry between the electric and the weak force is seen at our current energy level. These things were proposed, discovered, whatever you want to say, around 1973-ish, 60s to 70s, somewhere in there. And so basically, well, let me show you. I have some slides. So I would say there's a fair amount of like support for the electroweak theory because it makes some predictions that have borne out. There is a dream, it's always a dream of physicists to unify things. Like that's kind of the holy grail of physics, right? Is like this unification that we've seen in past epochs, you know, like gravity, the celestial and the terrestrial, the unification of electromagnetism, the unification of the electroweak. It turns out that you can play some games with mathematics, and it looks like you can like combine gravity and electromagnetism through something called the Kaluza-Klein theory. It doesn't quite work out. There's this infinite tower of momentum states or something that ruins things. But anyway, so this is the dream. Is like, you know, how can you unify forces? So one of the proposals is that. So I guess I should say the symmetry group of all this here. Well, I mean, I don't have space, but so let me just kind of recap the history here a bit. At the start of the 20th century, in the 20s to 1940s, we built what are called particle accelerators. We started to build things that made very high magnetic fields. And because it turns out that if you have a magnetic field and you play the right game, you can make electrons and protons, you can make them go really, really fast, right? And then if you slam these into each other, then they explode, basically, and they let this cloud of other weirdo particles out. And so we basically started developing the technology we needed to understand what the substructure was of protons and neutrons in like 1920 to 1940. We discovered that, so you guys can kind of ignore this. This is just like the backdrop. It's all quantum mechanics. Basically, to summarize what I'm saying here is that to describe a particle, you want something called a wave function. The wave function interacts with the Hamiltonian in this way. It interacts with the symmetry generators for your symmetry in this way. And the well, let me not. We don't have time for all that. This is all based on. This is all from Introduction. It's called Quantum Mechanics Symmetry, second edition by Greiner and Mueller. It's a great book, very understandable. A lot of exercises in there. I've also taken things from Introduction to Elementary Particle Physics by Griffiths, probably an edition, an older edition. Okay, so in short, for something to be a symmetry, it has to commute with the Hamiltonian. That's some linear algebra. And essentially, we find out that for physically interesting states, we can label them by this set of quantum numbers. All right, so finally getting to the point here. So those experiments I was talking about in the 1920s to the 1940s, we started noticing that if you look at neutrons and protons, first of all, they have almost the same mass. Neutrons and protons have almost the same mass. Anytime you see two quantum particles that have almost the same mass, that suggests an underlying symmetry, that maybe they're like kind of different versions of the same particle, and there's some kind of rotational symmetry between the two. And I say rotation in sort of a generalized sense. And so this defines isospin. Isospin rotates a neutron into a proton and a proton into a neutron. And there's algebra stuff here. And you can define the isospin of a proton to be 1/2 and the isospin of a neutron to be -1/2. These are called eigenvectors. So you guys study that in like Math 221 maybe? Well, definitely. We're definitely studying eigenvectors in Math 221, although not like this. All right, not like this, right? Who can testify? Ellie, testify. Not like this, right? No, okay, very good. So the neutron and the proton together form something called the isodoublet. But there's more. So people with these particle accelerators in the early 20th century, they discovered soon that there wasn't just a proton and a neutron, there was also the pi plus, the pi minus, the pi zero, and there were all these observed interactions. And basically, if you ascribe each particle having certain quantum numbers, you can see the conservation of these quantum numbers in the interaction. In other words, like basically, what comes in has to go out. In the same sense you guys are familiar with, like, if we start with, 10 kilograms of mass and we have a collision, we're still going to have 10 kilograms of mass afterwards, that kind of thing. Similar idea, but with quantum numbers here. And anyway, so there's this algebra structure that we see in the quantum mechanics. So that leads people to introduce something called hypercharge. Hypercharge is this sort of amalgam of the isospin that I was talking about and actual regular honest-to-goodness garden variety like charge, like the charge of an electron. And so it was seen that the neutron and the proton have like have hypercharge 1, and whereas the pi plus minus and pi 0 have hypercharge 0. And so we found that the particles are eigenstates of the charge operator Q with eigenvalues Q, and the charges. So this is the Gell-Mann-Nishima, I guess, relation. It reproduces the known charges of the neutron, the proton. All right, so fine. So people started making pictures of this. Once you start making pictures of this, all of a sudden it starts to become like a little bit more interesting because, see, these plots are very abstract. You're looking at a graph of isospin for the x and hypercharge for the y. So somebody had to think of inventing isospin and hypercharge to see these pictures, right? So the physicists who thought of these things, I mean, to me, they're brilliant. I mean, I don't know. I wouldn't think of such things. Certainly not. And so on the one hand, you have things that you've heard about before, right? The neutron and the proton, right? But those are just two aspects of a much richer structure, which is you've got these sigma particles, sigma 0, sigma, what is that? Sigma, I don't know what it is, sigma blarg, sigma naught, sigma plus. Maybe that's a minus. Probably minus. There's two things here. That's, I guess, the omega something or other, and 3 lines with a minus, 3 lines with a 0. Anyway, you've got all these. So the way to understand them is they're sort of like higher energy versions of the neutron or proton. These are all unstable particles, so like they'll radioactively decay back to the neutron and the proton after a very short amount of time. But they appear momentarily in these like particle colliding situations. There's also the meson nonnet, which you see these patterns, and there's the baryon decouplet. Baryon mesons have so there's two basic categories of particles. There's what are called bosons and there's what are called fermions. The bosons are the particles that have integer spin, like spin 0, spin 1, spin 2, like graviton is a boson, photon is a boson. The pi mesons are bosons. These are all bosons because they have integer spin. But the baryons are fermions. They have half integer spin, like neutron Proton, these are spin 1/2 particles, yeah? And electron is spin 1/2 as well. But here's the thing, this baryon decuplet, it has all these particles, and so these were observed, all right? So now we're in the 60s here, early 60s, and they kept building better particle accelerators because what else are you going to do with your science money, right? Build a better accelerator, and so do you guys see the pattern there? See that? See that right there? It just screams at you, there's another thing here, right? So this pattern was observed, and so then a physicist made a prediction that they would find a particle here with these properties. And they did, about 3 years after they made the proposal. So I don't know about you, like if you could imagine proposing a particle in 1961 and having it found in 1964, that must have been pretty exciting. So these people were like kind of into Eastern mysticism, so they've got some kind of nonsense about the eightfold way in here that has nothing to do with anything except the fact that there was probably some amount of recreational pharmaceuticals going on in this whole time period. But just guessing. But still good physics. Okay, so then what? So you see all these patterns, guys. Why are there these patterns? Why the patterns? There's obvious patterns here, right? Where are these patterns coming from? Jesus is ultimately the answer, yes. It's a very good Sunday school answer. So the answer rests in something called representation theory, which is something we don't have a class in here math-wise, because representation theory is essentially group theory, so like our abstract algebra class, paired with linear algebra. We have no such class here, all right? In fact, this, much to most physics departments' shame, is not a required course for undergraduates in physics, which is really stupid because to understand quantum mechanics, you have to understand representation theory, which is what this is. So anyway, long story short, you can, the patterns we were looking at are SU3 patterns. Essentially, they can be built from taking tensor products of SU2 patterns according to this algebra here. And I got some pictures. So like, basically, we can build this kind of pattern with these fundamental U plus, V plus, T plus things. And getting to the point here, I will get to the point. SU3 is rank 2, so this, again, I'm telling you things that I should not. Let me go on here. The picture is where it's at. So thus enter quarks. Quarks have a fundamental representation of SU3, either a 3 or a 3 bar, which means in terms of these hypercharged pictures, they look like this or that. And basically, you can build protons and neutrons from composite states of quarks. So like here's up, down, strange quarks, anti-up, anti-down, oh, there's something called an antiparticle. I forgot to tell you about that. Oops. Anyway, so here's the isospin, the hypercharge, plain old regular charge. Actually, not so plain. 2/3 of a charge, 2/3 of an electron charge, minus 1/3 of an electron charge, which I guess is 1/3 of an electron charge. Electron has like charge -1 in this system. So these quarks have fractional charge. We've never observed fractional charge. Charge is always integer multiples of the electron charge. This has been experimentally verified in thousands of experiments. We have never observed fractional charge, to my knowledge. And basically, there's a whole schemery, if you will, to keep these quarks hidden. They're always like behind the scenes. They're never observed on their lonesome. You never actually observe fractional charges directly. It's indirect, the reasoning we believe them. They all have something called baryon number, and they all have strangeness like this. But you put them together, and you can build the patterns we saw before. So if you take 2 quarks and you tensor them together, you can build this pattern, which gives us the nonnet that we saw. So all of those particles can be understood as being simply the combination of 2 quarks, which bear the appropriate quantum mechanical numbers. And to build the baryons, you take 3 quarks, put them together through very similar pictures, and you can build the baryon decouplet and so forth that we saw. And so, and here it is. So we can literally understand, yep. What is the circle? That's a tensor. It's a way of multiplying representation states. It's the mathematics that's needed when you have 2 particles that interact. They both have a symmetry, they both have a state vector, and when they come together and they become one state vector, the resulting thing is formed by a tensor. So, but in short, you see the neutron and the proton are built from 3 quarks. They're a particular way of combining 3 quarks. And so, while we have never observed a quark directly, this is why people believe quarks exist, because it's very striking that you can create all of these different particles that we've observed from a couple of basic quarks. It's an incredibly economical description of so many different particles. That's why people think there is such a thing as a quark. Now, again, there's something called quark confinement, which is one of the great standing theoretical problems of nuclear physics, is explaining how these quarks are confined. I don't know what the current state of the art is in that. I had a friend who was working on it. That's actually the origin of string theory. So one of the early things that was done to try to understand why quarks were confined was to just say, oh, well, they're stuck together with a string, basically. You've got one quark here, you got one quark here, they're stuck together with a string. They're stuck with a string. They can't separate. Because we know we can't observe the quarks by their lonesome, because the integer observation of charge is inescapable. Like, it's just experimental fact. So this led people to study something called quark strings. Now, this is not that widely known. I happen to have a friend who was working on it in nuclear physics. And it's kind of interesting. That's part of what led people to discover what's called string theory. Now, string theory is a much more speculative project to think about all of these things together as aspects of one single theory. String theory says that the quarks, the neutrons, the protons, everything is ultimately just vibrations on a string. Yep.
Picture up there, does
Yeah.
the EDB or do those just like cancel out basically, or where do they?
It's like a symphony. It has lots of different notes. They're all played at once. It's not one thing or the other. It's all of them, and they oscillate between each other. Something like that. No one can actually explain exactly the dynamics. This is another standing problem. We have this description, but there's this quantum chromodynamics. So quantum chromodynamics actually gives analogs for Newton's second law, which gives you equations which at the classical level the quarks have to satisfy. No one knows how to derive from quantum chromodynamics Lagrangian, like the bound states of quarks. There must be bound states of quarks. In other words, they have a stable existence where they're stuck together to make a proton and a neutron. There's 3 of them living together in some sort of like coherent orbit in the quantum mechanical sense, whatever that means, because neutrons and protons are pretty stable. Protons are very stable. People have been trying to prove protons aren't stable with increasingly expensive experiments for like the last 20 years. No one can prove proton instability at all. It's a problem because all of the exotic theories of matter predict proton instability, which we just don't observe. It's a big problem for people who have exotic ideas. Like, for example, supersymmetry. Supersymmetry is yet another unobserved symmetry that people want there to exist. Supersymmetry says that there's like this balancing between fermions and bosons. And if it's there, all kinds of, in calculus 2, how you have like alternating series that, when does an alternating series converge? It what? No, they usually do. Like, all it takes for the alternating series to converge is that for the terms to get small. Like, if you have, in the regular series, terms get small, it doesn't tell you anything. They can still blow up. Like, the 1 over n thing always gets you guys, right? Like, sum n equals 0, n equals 1 to infinity of 1 over n. Converge or diverge, you guys will be like, limit as n goes to infinity of 1 over n equals 0. It converges, therefore series converges. No, you've fallen into the quintessential trap of calculus 2, right? That's the harmonic series that diverges. For alternating series, when you've got that plus minus, there's this natural cancellation which makes intuition sort of more come to bear with the convergence. Supersymmetry is something similar. It tends to be the case that that bosons have like a plus and fermions have a minus, roughly speaking. So in places where you have series, those series will converge much more naturally and nicely if there's supersymmetry, which is why people want supersymmetry for theoretical reasons, because it just makes the math fantastically easier. Like there's all kinds of things we can do theoretically with supersymmetry that we just cannot even hope to accomplish without it. Einstein, the better part of the last of his life, was trying to work on a unified field theory without supersymmetry. He made no headway on it, despite spending decades on it. So it's pretty well understood that without supersymmetry, like unified field theories are really, really hard to do. Supersymmetry makes things fall out really nicely. Now, string theory is not a single theory, it's a theory of theories. I'm not trying to tell you like it's physically reasonable or anything like that. I'm just telling you that for the better part of the last 50 years, theoretical physicists have been like stuck on string theory, trying to understand it, right? You've seen the Big Bang Theory, right? No? That's good, don't watch it. But string theory is this sort of it's hard to define string theory because it reinvents itself about every 3 years or so, at least it has for a long time. And I think it's very interesting, but it also doesn't really make any physical predictions much to speak of at the moment. Besides, it does do some things about like quantum states of black holes or something like this, maybe. It may have something to offer in something called the ADS CFT correspondence. There was something hopeful there, but I'm not sure how that panned out. Anyway, I do think there is such a thing as quarks. I mean, roughly speaking, I think these things are all approximate, right? I mean, I think like, to me, God allows us to understand, the universe in stages, right? None of these are really the complete reality in my view. We just, we see through things dimly. Later, face to face, Anyway, so the other thing I would mention is the string theory is, one of the dreams of string theory was that it would be like self-proving, that like there would be a unique string theory that mathematics would demand it be what it was, and that has just been shown to be false. String theory has like an innumerable amount of possible starting points. Like you can give tons and tons of different initial conditions and create all kinds of different universes. One of the games that's played is to put it on what's called a brane, and if you pick a particular brane, you can kind of reproduce the standard forces, the four forces symmetry groups at least, in a certain sense. So there, I don't know, you could spend your life and still not get to the end of it, Okay, so we have a test coming up, I guess, which is what? The final exam? What should I put on there? Just kinematics? It should just be dot products? But what if you guys give me a dot product as a vector? What then would I do? I would have to fail you, right?
Probably.
So if you guys put a dot product as a vector, do I have your permission to fail you on the final?
Yeah.
No? Yes? I hear some yeses.
Get it right.
Oh, if you get it right, I have to pass you? No. So joking aside, the final exam will be an amalgam of test 1, 2, and 3, and a combination of test 1, 2, and 3, and there'll be like a token question or two about the stuff we talked about the last week. But basically, I just ask a question to see if you're paying attention. So if you've been paying attention, you should have no problem with that. It's not going to be a lot of points. Don't stress about it. Stress more about figuring out what went wrong in test 1, 2, and 3. That would be my advice, right? So, oh, there's a sign error in the force calculation in test 3. I didn't distribute a minus correctly in part E, I think. So just watch out for that there. Anyway, it's been fun. If you guys didn't get your tests or old stuff, there's stuff over here. So please avail yourself of the stuff. Have a good summer.